Hi everyone, my name is Charlie Mpetha. I'm a graduate student currently based at the University of Waterloo. And I'm going to be telling you about this project I've been working on with James Taylor on using the Infall region around galaxy clusters as a cosmological probe. So galaxy clusters are the largest gravitationally bound structures in the universe, and each one will have an associated dark matter halo. And that's what I've plotted here. We have the density profile of one of these dark matter halos. On the x-axis, we have the distance from the center, and on the y-axis is the density. And I've split this into three different regimes. There's the inner profile on the left. This is bounded by the virial radius, which is the black dotted line, and all material within this virial radius is virialized, so we can say that it's gravitationally bound to the halo. Furthest to the right, we have the environment, and this is demarcated by the turnaround radius. That's the point where the Hubble flow dominates over the gravitational attraction of the halo. So any material in the environment is not gravitationally bound to the halo. And then there's this in-between region, which we call the infall region. This is where material is being drawn in from the environment and falling into the halo. And this is the region of interest in this study. I've marked off two specific features of the infall region, the splashback radius in the orange triangle and the depletion radius in the green star. And I'll explain what each of these is in turn now. So the splashback radius, this is the point at which material builds up after it's completed one orbit of the halo. So it falls in, orbits once, and then builds up at the apicenter of its first orbit. And this large buildup of material creates a very sharp drop in the density profile. You have lots of material and then not much, so you have a sharp drop. And so we can identify this splashback radius using looking at the gradient of this density profile, and the minimum of this gradient will be the splashback radius. So that's what we see in these lines here. And we see that for larger cluster mass halos, the splashback radius is a very prominent feature because these accrete a lot more material. And for galaxy mass halos, it's a less prominent feature, but it's still present in the density profile. Next, we have the depletion radius. This can be understood by considering the bias profile of a dark matter halo. This is the ratio between the halo matter correlation function and the matter matter correlation function. So we can kind of think of it as the relative overdensity of a dark matter halo in its environment or in the background overdensity. We see that for lower galaxy mass halos, the bias profile has this very prominent dip. And this is because there's a region around these halos where matter has been very depleted because it's fallen into the halo and the background overdensity is quite high. And so we have this relative region of depletion. And the depletion radius is the minimum of the bias profile or the most depleted region around a dark matter halo. For cluster mass halos, we don't have this very obvious dip. And the reason for this is clusters tend to live in already very overdense environments. And so you don't have this large dip in the bias profile. So just an interesting note, we see that for the depletion radius, it's most easy to observe in lower mass halos. But for the splashback radius, it's most easy to observe in cluster mass halos. So these are two kind of complementary measures of the infall region, spanning a large range of halo masses. So to create these plots and the results that you'll see soon, I've used a suite of 21 cosmological simulations created by Yuba Amore. And each simulation has a different combination of omega m and sigma 8. And the different combinations can be seen in this table at the top. At the bottom, I've taken the two cosmologies at the top left and bottom right corner of this table, and I've plotted a stacked dark matter halo. So this is for galaxy clusters, so using all halos with a mass greater than 10 to the 14 solar masses, stacking their profiles to create this smooth isotropic density profile, and from there finding the location of the splashback and the depletion radii. And the key point of this figure is that we can see there's a large difference in the depletion and the splashback radius in each of these two cosmologies. So we see that it exhibits the strong cosmological dependence, and that's what we hope to take advantage of if we can find a similar set of observations of galaxy clusters in the universe, measure their splashback or depletion radius, and compare that to what we expect from simulations. That gives us a way of probing the true values of these cosmological parameters. So just to emphasize that point a little bit further, here we see a plot of the halo mass on the x-axis versus these different radii on the y-axis, where the blue dashed line is the splashback radius and the green solid line is the depletion radius. And the color of these lines corresponds to the value of S8 in this simulation, where S8 is this specific combination of these two parameters, sigma 8 and omega m. And this just shows that there is a strong dependence of these radii on both mass and cosmology. And also overplotted is lots of values from the literature of the measured splashback radius in observations of galaxy clusters and lower mass halos, and also the one example of measurements of the depletion radius. And so we see that our simulations are broadly consistent with these observations. And you can also see that observations so far are not well measured enough to constrain the specific values of sigma 8 or omega m, because they tend to span the whole range. But with upcoming weak lensing surveys, that can be possible. And that's what I'll start talking about now. So in this work, we assume that halo profiles are measured via weak lensing. So the way this works is you know where your foreground lens is, your foreground galaxy cluster, and you look at the galaxies in a weak lensing survey in the background behind this galaxy cluster by measuring the shapes of these galaxies and looking at how these shapes are distorted by the gravitational potential of the foreground lens. Then that gives you an idea of the mass or the density profile of this halo. And so by looking at it as a function of angle from the distance to the center, then you essentially look at the density profile or a proxy for the density profile at larger and larger radii from the center. And that's what we can use to measure the profiles of our dark matter halos. Within this work, we've produced forecasts for two weak lensing surveys. One is a more present survey, that's the Unions survey, which is a large ground-based imaging survey, which expects to have 10 sources per degree squared over nearly 5,000 degrees squared on the sky with this shape noise. And we also look at Euclid, which is a slightly more near future weak lensing survey covering a larger sky area with more sources and a better shape noise. So these are kind of like two different regimes. One's more constraining, one's less constraining, and it'd be interesting to see what's possible with these two weak lensing surveys. The number of lenses that we assume, so the number of galaxy clusters in the foreground, are shown in this table in the bottom right. So Unions is lower redshift and lower mass, and Euclid is higher redshift and higher mass. So now I'll just talk a bit about how we go from the simulations that I described earlier to mock observations, to mock shear profiles in these weak lensing surveys. So we start with the density profiles from the simulations, and that's in the very top left figure here. And again, I've plotted these two different cosmologies that were on the either end of that table, top left and the bottom right corner. So first, we take these profiles and we can find the splashback radius and the depletion radius. And we already see there's a large difference between cosmologies in these two radii. And then we convert these density profiles into what's called a delta sigma profile, which is a proxy for the density profile. It's the 3D density profile projected into 2 dimensions. And we find the mass profile of these halos. And then we convert this into a shear profile, where the relation between delta sigma and shear is seen in the bottom right. And this sigma crit parameter just depends on the details of your weak lensing survey. And so this bottom middle figure shows these mock shear profiles, and the gray band, this is the infall region that we've already talked about, and we see the splashback and depletion radius highlighted. And so we see that within this infall region, the actual amplitude of the shear profile itself is significantly different between these two cosmologies. And then finally, we create our mock observations by using details of the source and lens catalog to create error bars on our shear profile, and we add some Gaussian scatter based on these errors. So that's how we go from our initial density profiles from simulations to our mock observations that we can then use to test how we can use these observations to probe cosmology. So I'll just describe the process by which we use these mock observations to get forecasts for cosmological constraints now. So here we see a shear profile in this cosmology here, where omega m is 0.3, sigma 8 is 0.85. So we have our data points, we perform some fit using a 3D density profile, and this is a density profile model from a DEMA 2023 paper, which has 2 different terms, one describing the orbital term or the inner region, and one describing the infall region. So this density profile has been designed to very precisely fit the full shape up to large radii. So we perform this fit, And then once we have our fitted density profile, we can use that, well, with some error bars. They're actually maybe too small to see, but there are some shaded bands around this best fit. Once we have our fit and errors, then we can use this to find splashback radii and depletion radii. In the splashback radius case, we take the derivative. And depletion radius case, there's some extra, more complicated steps to try and extract this bias profile with its uncertainties. And so the shaded bands here give 1 sigma errors, and we can see that the errors are small, but not insignificant. And so the key question here is, are these errors on these features of the infall region smaller than the variations due to cosmology that we see, for example, in this figure here? So if the errors are smaller than the variation due to cosmology, then we can use this measurement of the splashback radius in galaxy clusters to place some constraints on the values of omega m and sigma 8. And so that's now what we're looking at here. So these whisker plots show on the x-axis the splashback radius, and on the y-axis all of the different simulations that we consider. So the different combinations of omega m, which is the number on the left, and sigma 8, which is the number on the right. And so for each simulation, we stack our dark matter halos. We find what's the true value of the splashback radius. That's the small green lines here. And then we produce our mock observations. We fit these with the fitting process I've just described. And then that gives us our black data points, which are the fitted values of the splashback radius with the associated uncertainties. So we see that in unions, the error bars are larger than the variation due to cosmology. So therefore, we cannot expect to constrain cosmology in unions using the splashback radius. However, in Euclid, the error bars are a lot smaller than the variation due to cosmology. And we actually find that the splashback radius on its own can constrain omega m and sigma 8 by around plus or minus 0.05 as an independent probe. This is already looking promising as, using the infall region as a test. And one final detail is I've highlighted the cosmology in our simulations that's most similar to Planck, and that gives the magenta band there. So you can imagine if, for example, we observe a splashback radius with this value close to 2, then we can constrain a deviation from Planck with around 3.6 sigma. So just to give an idea of the possibilities of this method. So unfortunately, we see that for the splashback radius in unions, because there's a few steps to obtain this radius. First, we need to perform the fit, and then we need to take the derivative. This very much increases error bars, and so we can't perform these constraints. And we also find a similar case for the depletion zone actually has even worse constraints. So one of the conclusions of our work is that the depletion zone is not a viable method for cosmological constraints, just based on the different steps needed to obtain that radius from your observations dilutes error bars too much. So we asked, is there something better that we can do? Instead of performing all these fits onto the shear profile, which makes it noisy, can we do better? And the answer is yes, by not even attempting to fit the shear profile, but just looking at the amplitude itself. So in the top plot here, we see the contour from Erisita, and the 2 stars give cosmologies kind of closest to the top right and top left corners of this contour. And so we're asking the question, can we reduce the size of this contour by constraining the difference between these 2 cosmologies? And so in the bottom plot, we see the shear profile in these 2 different cosmologies. Once again, the infall region is the gray band. And so we can see that the shear profile in the infall region is significantly different in these 2 cases. The signal is greater than the noise. And so quite a simple test would just be to find what's the average shear within the infall region in these 2 cases, and what's the uncertainty on that shear, and can we compare these? What's the signal to noise of the difference? The amplitude and the noise, and the amplitude and the noise, and can this amplitude of the shear profile itself be the cosmological probe? And so that's what we're showing here in unions and Euclid. And we see by just looking at the amplitude of the shear profile, that very much improves our constraining power using this approach. And we see a good signal to noise ratio is possible using both unions and Euclid, where in Euclid, we can obtain very strong constraints on omega m and sigma 8 just by comparing the amplitude of the shear profile. just to kind of illustrate that point further, here we've placed the same results here, but instead as contours in this plane where we're comparing the shear profiles to the cosmology of omega m 0.3 and sigma 8 0.85. So these contours, this is assumed to be the true cosmology, and how well can we constrain deviations from this? And that's the contours that you see here. And so one really great thing about using the infall region as a probe is that the degeneracy direction, or the dependence of the infall region on omega m and sigma 8, is nearly orthogonal to the S8 degeneracy, which you see in these error zeta contours. So by using these two independent probes, number counts, and using the infall region and combining them, then we can significantly reduce the uncertainties in both of these parameters because of these different degeneracy directions. And so that's a really neat use of this infall region as a complementary probe. The main caveat of this approach is because we need to have a very representative sample in our simulations to compare to our observations, then we need to know the masses of our observed galaxy clusters with relatively high precision. And mass estimates of galaxy clusters is a tricky issue. It's a non-trivial problem, and so that's the key kind of caveat of this method. But given that you can obtain good mass estimates of large numbers of clusters, then the infall region promises to be an excellent complementary probe of cosmology. So just to conclude, we've demonstrated that with Euclid weak lensing of galaxy clusters, Euclid weak lensing profiles of galaxy clusters, splashback radius can be a valuable cosmological tool. We've shown that measuring the observed shear profile directly is actually a better test, and with both unions and Euclid, we can obtain good constraints on omega m and sigma 8. And the key result is we've shown that it's complementary. So the degeneracy direction is nearly orthogonal to that from cluster counts. And so combining these two methods is a great way of obtaining better constraints on these two parameters. So just a couple of points for future work. One is we can investigate some optimal filter of the infall region. So instead of just taking a radial range and just finding the average, we can try and best extract signal to noise from the infall region. And finally, we plan to perform this analysis using galaxy clusters in the union's footprint to see how well this method works with real data. Thanks for your time. Looking forward to chatting in the asynchronous discussion.